Hey ladies and gentlemen, we are excited to share our work accepted to ECCV 2024 on the topic of stereo image compression. With the development of hardware facility and software algorithm, the widespread of binocular cameras and stereo vision has expanded our 2D vision and entertainment into stereoscopic and 3D. A lot of applications show great booming relying on stereo images, like AR/VR devices, known as the popular headset Vision Pro, and other applications autonomous driving, surveillance systems. However, storing and transmitting large volume stereo images pose dramatic challenges. Therefore, we are motivated to develop stereo image compression algorithm, boosting the application and usage of stereo vision. We know that single image compression has been widely studied and adopted. However, stereo image compression has many unique properties. When compressing stereo image, we need to dig into both the inter-image features and inter-image features. It is critical to consider how we model the mutual information or correlation between stereo views. Directly applying single image compression method on stereo image compression task obtains suboptimal results, which motivates us to explore methods specifically designed for stereo image compression. Among previous stereo image compression methods, the unidirectional compression paradigm is usually adopted. As shown in the graph, one view, for example, the left view is compressed independently. And then the residual of left view and right view are calculated and compressed. In this method, the stereo views go through different signal processings, yielding different compression quality, which is disadvantageous for visual experience and downstream tasks. Compared to this unidirectional method, we advocate bidirectional compression, taking both views together in a symmetric way. In this method, the two views are compressed symmetrically, obtaining balanced quality. Here we illustrate the pipeline of our proposed bidirectional stereo image compression. The joint encoder, composed of 3D convolution layers, takes the stereo views as input. The downsampled latents Y left and Y right are fed into the hyperencoder to obtain the hyperprior to model the distribution of the latent Y. Later, the hyperprior is used in the proposed cross-dimensional entropy model to obtain accurate probability distribution of the latent. In the following, we introduce the modules in the whole pipeline in detail. To enhance the stereo features, we design a two-stage, symmetric mutual attention block, inserted between the 3D convolution layers in the codec. As shown, in the cross-key attention stage, for each view, we generate an attention map using its key and the value from the other view, which is then queried by the current view. This stage facilitates inter-view alignment and the identification of common patterns. In the cross-query attention stage, the attention map is obtained using the key and value from a single view, and then queried by the other view. This process preserves the individual self-features of each view, while the other view serves as a reference for determining the allocation of attention weights. After that, we employ a refine block to get the desired output. This bidirectional mutual attention block is suitable for any stereo information transfer scenarios, making it a generalized plug-and-play block. For data compression methodologies, entropy model is critical to estimate the latent probability distribution, and an accurate probability distribution guarantees compact entropy coding bit stream. Our proposed cross-dimensional entropy model aggregates hyperprior, spatial context, channel-wise context, and stereo dependency. For the hyperprior component, we generate the dependency Z from the hyperdecoder HS. For the channel-wise context, we evenly split the latents on the channel dimension into K slices, and exploit the strong correlation on this dimension, considering both stereo views. For the spatial context, masked 3D convolution is utilized to obtain stereo spatial features from both views. After capturing the cross-dimensional dependencies on multiple axes, we aggregate them to obtain a distribution estimation, which are further utilized supporting the estimation for later slices in an autoregressive manner. Here we show the rate distortion performance of our method, implemented on two datasets, in stereo 2K and cityscapes, evaluated with both PSNR and SSIM, compared with previous classical codecs and advanced learning-based methods. From the rate distortion curves, our method achieves state-of-the-art performance compared with other methods. Here we illustrate the visualization of different compression pipelines. Our method obtains the highest PSNR with relatively lower BPP. We can tell that our bidirectional design enables a balanced compression quality. The discrepancy between views is only 0.3 dB, proving the advantage of our bidirectional design. In conclusion, in this work, we discuss about how we are able to dig into the inter-image correlation between stereo views, and our work presents an effective solution for bidirectional stereo image compression, reaching state-of-the-art performance. That's all for our work on ECCV 2024. Thanks for your interest. Should you have any question, please contact us.